Hello, today we do the last experiment number 12, heat of a reaction. Heat of a reaction is generally defined as the amount of heat released when 1 mole of an acid reacts with 1 mole of a base. And it's represented by its units as kilojoules per mole. This means that we always express the heat of the reaction in terms of the limiting reagent if the solutions are mixed together. And in this experiment, you will be measuring the heat of reaction between 1 molar HCl and 1 molar NaOH. Again, the concept is the same. When two acid and bases reacted together, heat is released, and this heat released is used to warm up the solution as well as heat up the calorimeter. However, since in the experiment in simulation labs, you have a calorimeter, and the calorimeter constant is generally given to you, then there is no problem in calculating how much heat was gained or lost. However, before I start the experiment, I'm going to just show you in a document format how to calculate the amount of heat, the calorimeter constant, because it is important to remember that a liquid cannot be kept just plain by itself unless within a container. And therefore, after that, I'm going to show you how to perform the experiment. In a small quantity, show you how to take out the graph is obtained for this particular experiment using a simulation lab, and after which you can solve the problem and complete the calculations. So I'm going to share now my Word document here. How to determine the calorimeter constant. This section is really important because you need to know how to do it. The calorimeter constant can be determined by using the law of conservation of energy, which states that energy can neither be created nor destroyed. Therefore, the heat lost by a system must be equal the heat gained by the system. And just like in the previous experiment, heat lost is given as minus mc, that is the mass times the specific heat of the material multiplied by the change in temperature. The change in temperature is, because the sign over here is negative, we can always write the change as equal to delta T is equal to T initial minus T final. But always remember that whenever the term symbol delta comes in, it's always T final, take away T initial. Now the heat gain during the reaction will be the heat gained by the cold water as well as the calorimeter itself. And the change in temperature for both the cold water and the calorimeter will be the same because the water is kept inside the calorimeter. So if we know the mass of the water and the specific heat of the water, then we know how much heat was gained by the cold water. Now, the heat gained by the calorimeter, we cannot find out. But what we do is we get the term called as the calorimeter, which is simply the specific, which is simply the heat capacity of the calorimeter. Because mass multiplied by the specific heat gives you the heat capacity. And therefore, if we know the heat, the Q, or the heat lost by the hot water, and the amount of heat gained by the cold water, then that difference, if you divide it by the change in delta T for the cold water, you'll get the calorimeter constants as shown here. Remember that the sign of heat lost is minus MC delta T because I'm using the rule that delta T is equal to T final minus T initial. But if you flip it around, then it becomes T initial minus T final. And that is how you can put it in and have the correct sign in place. Next, I'm going to share my experiment with you from the simulation lab. Now, again, over here, please read through the introduction. And very, very simply, in 2 lines, I'm going to give you. The law of conservation of energy is actually a statement to the first law of thermodynamics that energy can neither be created nor destroyed. Also, the first law can be explained in mathematical terms as that Q is equal to U minus PV, where U is the internal energy and PV is the work done. Because these particular experiments were done using equipment or machines. Now, H then at constant pressure symbolizes what we call as the enthalpy change. We can never find out what was the initial enthalpy, but we can always find out the delta A, that is the change in enthalpy, is equal to delta U plus delta PV, the work. Now you will see that U, P, V, H are all written in capital letters. That means they indicate state functions. State functions are those functions that depend only on the initial and final values and not on how it was reached. So using this expression, then we can get that Q reaction is equal to sum of the heat of the solution plus that of the heat gained by the calorimeter, because the experiment is done in the calorimeter. Once we know the moles of the reagent that you have taken, or which is the limiting reagent, then the Q reaction divided by the number of moles of the limiting reagent will give you the delta H per mole. The units for delta H, the enthalpy change at constant pressure, is kilojoules per mole. After this, I'm just going to go and show a brief demo for the procedure. Read the procedure by yourself, but here is a demo of it. So I'm going to take, first I'm going to locate a calorimeter. So there you have the calorimeter. Inside, right-click the calorimeter, go to the chemicals, and add, I'm just going to add 20 mL of 1 molar hydrochloric acid I've added. Then I'm going to insert a thermometer so that you can read it. And next, I'm also going to add a pH meter. So I've got all this set up, that is in terms of the calorimeter. After that, I'm going to get a burette, a 50 ml burette. And here I'm going to put the 50 ml burette directly on top of the calorimeter. Let me just remove the thermometer for the time being so that we can put in the liquid. Then I'm going to chemicals and add, say, the required sodium hydroxide. And I'm just going to put 25 mL, but you will take the volume that is stated in your procedure. And the strength of the sodium hydroxide is 1 molar solution. So now now what I'm going to do is, I've kept the titration dialog box so that you can see it beside. And then I'm going to click on the right click and get a pH meter. Oops, right click I got the pH meter, and then I'm going to right click again to collect the data. Again, right click on the pH meter, and I'm going to say view the graph, the table, titration data. If you look at the titration data, there is file, edit, and view. If you go to the edit, you can copy this particular screen, this shot that is of the pH graph, and place it onto your lab report. Now, under the view, there are three subtitles: graph, data, and refresh. So we are going to make sure the graph is highlighted. I'll show you the data later on, what you can get from it and why. If you need, you can copy that and paste it onto an Excel sheet and have the graph plotted over there too. Since you're freshmen, there is no need to do that. But when you plot the graph, as you will see, I'm going to now I'm going to start the stopcock. As you start the stopcock, we are starting at 25. I've just started, not at 0. I just want to see. And as you can see on the titration curve, you see 2 lines. One is a red one, and another one is the black one. The black one represents the pH, and the red one represents the temperature. And you can see as the experiment is going on, you will see that the screen, the time slot is moving as the amount of NaOH is added. And you see also that the thermometer temperature is rising. And watch it. And as you look at the black line now, you can see that the pH is slowly increasing. Now suddenly it has reached a maximum. And then we generally try to add a little bit of excess so that you can see the curve that is there. So from this particular graph, you see one thing is that it is an S-shaped curve. The neutralization point is about, it should be around about 7, but you can see what it is giving over here. And then you can get the maximum temperature from here. Once you get the maximum temperature, you know what was the initial temperature. You can read it out of the graph as 20. Then you see it is between 26 and 27. So now we don't know exactly what the temperature is because we do not have this small fine divisions on this. In order to find out exactly what this is, first make sure you copy this and paste it in your Word document for the lab report. Then you can go to the data. As you go to the data, you go on adding. So check out, this is the volume of ml added. So it's not from 0, but it goes from 25 onwards. And then as you go down, you will see that at one point, can you see here, between 19 and 20, there is a sudden jump from 2.60 to 11.39. And this is for my reading, but not for yours. Yours you will have to check. And so this will give you the exact change in the reading that was obtained and the pH and the middle document shows the pH and the exact change. And use this to calculate your enter in your observation and complete the calculations, because you know that Q is equal to MC delta T, and then using the values of M, C, and delta T with the assumption they have given what the density is and what would be the mass of the solution, what is the density of the solution, and what is the specific heat of the solution. You can calculate your delta H per mole of the limiting reagent. And with that, I'm going to stop the share.